that I'll include in my program in order to generate frequency distributions. I have the names of each of the variables circled here in red. Here is an example of a NESARC program with the frequency procedure and table statement added. Then a run statement is added at the end of the program. The run statement is responsible for executing all the previously entered SAS statements in this program. When you add a proc, freq, and table statement with your own variables of interest from the data set you have chosen to ask your research questions about, and then conclude with a run statement, you have written an entire SAS program. You will build on this program as you progress through your project. Before you run the program, it's always a good idea to save it. Click the Save button at the top of the program window. After you save the program, you can run it by clicking on the Run button at the top of your program menu. The Run button is the second icon button from the left. SAS Studio has 3 different tabs located at the top of the main program window. You write your code on the page marked by the Code tab. Just to the right of the Code tab is the Log tab, and to the right of that is the Results tab. Once your program is finished running, either the Results tab or the Log tab will open. It's a very good habit to get into to check your Log tab first after running a program, so you can check for any errors in your program. When you click on the Log tab, you will see a section at the top of the page entitled Errors, Warnings, Notes. If any errors were detected in the program, the number of errors, located in parentheses, will be listed to the right of the red X Errors icon. The same with any warnings or notes. If there are any warnings, the number will be listed in parentheses to the right of the yellow triangle Warnings icon. And any notes SAS has about your program will be numbered, again in parentheses, to the right of the blue eye circle Notes icon. If you double-click on any of these icons that indicate the number of errors, warnings, or notes that exist in the program, then a list will appear beneath the double-clicked icon. If you do find any errors listed on the log page, go back to the code page, correct the errors, save the corrected code, and then run your program again. If no errors are listed on the log page, click back to the Results page and you will see the results of your program. In this case, it will be the distribution tables you generated. In this example, my program has run successfully and the notes, listed in blue font, tell me a few things. It tells me the reference library, which was called My Data, was successfully assigned. Also, there were 43,093 observations read from the data set NESARC. That's good news, since I know that is the number of observations or individuals in the data set. If the number of observations seems incorrect, it's possible there may be a problem with the program that processed the data incorrectly, rather than actually generating an error message. If your program ran successfully, and there are no error messages in the log, then go ahead and click the Results tab to see the frequency tables that were generated for each of your variables. Because the actual variable names are cryptic, it's a good idea to give them labels that are more easily interpreted at a glance. We will use Lisa's NESARC program again as an example and show you how to generate variable labels in your program. SAS programs are made up of 2 distinct steps: data steps and proc steps. You write data steps, which enable you to manage and manipulate your data. You are writing code telling SAS exactly what to do with your data. Proc, or procedure steps, enable you to analyze and present your data. Proc steps are pre-written procedures. So the code in the proc step is not giving SAS instructions to execute like the code you write in a data step does. The proc codes you write basically control how the proc step runs. With this in mind, you're going to enter your label statement here. Labels require the use of the term label. Then you enter your variable names. Each variable name is followed by an equal sign, and then the new descriptive variable name within quotation marks. Once you've completed the list of your new variable labels, this label statement, like all SAS statements, ends with a semicolon. Then save your program and rerun it by clicking the Run button. Check the log, which shows no errors, and then view the results. Now the frequency distributions include both the variable name and the variable labels. Look at the first table, which shows the distribution of responses for the variable tobacco dependence in the past 12 months. The NISARC codebook shows that 1 means yes and 0 means no. The first column of response options, 0 for no and 1 for yes, is followed by a column that shows the frequency of each response. The table also shows the percent of individuals with and without nicotine dependence, the cumulative frequency, and the cumulative percent. By consulting the codebook, you can interpret and describe each of these frequency tables in the same way. Once you have examined frequency tables for your variables, the next decision you need to make is whether you want to subset the data and ask a question based on specific observations, or whether you want to ask the question of the entire sample. In other words, are there particular rows in the data set, that is, individual observations, that you want to keep and others that you want to exclude? For example, Lisa is most interested in the association between smoking and nicotine dependence in young adults who may still be establishing their smoking patterns. Therefore, she decided to examine only those adults who are 25 or younger and exclude all adults older than the age of 25. At this point, I want to find the age variable in my codebook. I also decide that I want to focus on recent smokers rather than individuals who have smoked more than a year ago. To implement these decisions, I will go back to my program and add 2 additional statements just before the end of my data step. These additional statements are logic statements. Specifically, you need to add logic statements that will tell the program to include only those observations that will help you answer your research question. Using Lisa's research question as an example, it is now further clarified to include the association between smoking and nicotine dependence, but only among young adults who have smoked in the past 12 months. The research question is not changed. Rather, the question will be asked based only on a subset of the observations that are available in a specific data set that will help answer the research question. Logic statements require 1 or more operations. Here's a table of common operations used in SAS. These include equal to, not equal to, greater than, less than, greater than or equal to, and less than or equal to. The following logic statements will need to be added to this program in order to call in the specified subset of the observations now to be used as the basis of the research question. If check 321 equals 1, semicolon, which is the variable for cigarette smoking status in the past 12 months, and if age LE 25, semicolon, indicating selection of only those individuals less than or equal to 25 years old. These logic statements go at the end of the data step before the proc sort statement. The variable age should also be added to the table statement so that distribution can be examined. Now, when this program is saved and rerun, you can see frequency distributions for each of the variables, but only for the 1,706 individuals aged 25 and younger who reported smoking in the past 12 months. I can be confident that I am now working with this sample because, as you can see, all of the 1,706 observations has a 1, meaning yes, for having smoked in the past 12 months. And if I scroll down to the distribution of age, I can see that only 18 to 25-year-olds are included in the sample. If, for your own research question, you are completely unsure at this point whether or not you want to limit your question to a subset of observations, no worries. In that case, there would be no need for you to add any additional logic statements to your program. This is always a decision and an example that you can revisit in the future. Here's a way to add notes to your program to help you remember what specific lines of code do. As you keep adding to your code, it might become difficult to remember why you wrote what you wrote. You can comment out your notes so that SAS does not read the notes as actual program statements. The method for doing this is to include your notes in between a /* and a */. Here's a note Lisa added to her example code. She is reminding herself that she is subsetting the data to include only past 12 months smokers age 18 to 25. The cursor is listed in green within the program. You can be confident that it will not be read as SAS syntax. You should definitely use this commenting out technique early and often as you build your program. These notes can be very important because they will help you keep track of decisions you've made and actions you've taken in writing your code. At this point, and whenever you've added something to your code, you should save it. You now have the tools you need to complete assignment 2. For this assignment, you should write a SAS program that displays frequency tables for the variables that you've selected for your research question.